Welcome back to 8701. So in this lecture, we open a new chapter, the weak interaction. So we are one by one adding together the components we need in order to describe all elementary particles and their interactions. So now we're adding the third form of interaction. After the QED and QCD, we enter into the discussion of the weak interaction. So let's have a look at the standard model. So we discussed gluons and QCD, and we saw that gluons couple to themselves and also to all quarks because they carry a charge under QCD, a colored charge. We have also discussed the photon and seen that the photon, they do not couple to themselves, but they couple to all charged elementary particles. Those are the matter particles, the fermions. The photon also couples to the W boson because it's electrically charged. So now what we want to do in this next chapter, I want to fully understand the W and the Z boson. And we will see that they couple to all matter particles. And we'll also discuss how they might couple to themselves, or the Z boson couples to the W boson, for example. So that's the story of this entire chapter, and we'll take it one by one. As an introduction, we start with the Feynman rules. So having the Feynman rules in place and the cookbooks, the recipe in order to calculate decays and scattering processes, this is all we need in order to get moving. Okay. So we can, for example, look at this vertex here, or this component of a Feynman diagram. And what we need to analyze this is the propagator for the W and Z boson and the vertex vector. So this vertex vector now looks a little bit more complicated than for QED and QCD, because the W boson and the Z boson, they carry mass. Okay, so we have those additional factors, Q square minus M square, and this Q square over M square term as well. Okay. One interesting fact about this vertex vector is what happens now if Q square is much, much smaller than M square, right? Basically get rid of those components here, and we find a vertex vector which looks similar to the one we have in QED. However, there's no 1 over Q square term, but just a 1 over M square term, which is constant. So we will see that we can describe this in the context of the Fermi theory, which is a low energy approximation of the full theory of weak interaction. It's kind of an interesting concept, and it extends to the entire understanding of the standard model. It might be that our standard model, when we have all the packages together, describes a lower energy approximation of a more complicated, more holistic theory, which we then can discuss under the concept of a ground unified theory, maybe with a symmetry group, which is embedding the symmetry groups we need for QED, QCD, and the weak interaction. All right, but that's a side remark. So we look at the Fermi theory a little bit more later. The vertex vector itself, describing the vertex here, is given here for the W and W boson and also for the Z boson. And it looks a little bit more complicated than the vertex vectors we have seen so far. So what you note is that there is a parameter which is associated to the strength of the interaction, but there's and the gamma matrix, but there's also this term here, which has two components. There's a 1 and there's a gamma 5 matrix. All right, we have talked about gamma 5 matrices already. We can later identify those as individual currents coupling to vector current and an axial current. So this looks even more complicated now for the Z boson, because here we have not just numbers of 1, but an additional factor. This factor CV is a vector coupling, and it's specific for each fermion. So each fermion has one of those constants. And there's a second part of package or set of constants for the axial current. You have a second parameter here, which is the strength of the coupling of the Z boson. So at this point, we just take this for granted and we can do our calculations. And on the next slide, I'm going to explain to you what the corresponding numbers are, what those values are for those parameters CV and CA. Later, we will see how it comes to this more complicated structure and why there is a vector and why there is an actual axial current in the weak interaction. But for now, we just take this for granted and we just take this as a recipe. So now for the neutral, so we just have seen that this is the vertex vector. And here for all fermions, we list what these values are for CV and CA. What you can see is, okay, for the neutrinos, the factor is 1/2, both for CV and for CA. And for the charged leptons and quarks, there's an even more complicated term here, which includes the new parameter, sine square theta W. The value of this is 28 degrees. Sine squared theta W is 0.231. As a little bit of a preview here already, the fact that there is this new parameter and an angle involved leads to, or can be explained later by the fact that the weak interaction is actually a result of a mixing between an original weak interaction and QED. So there is a mixing going on. In other words, the Z boson itself is a mixture between the thing which couples to the weak part of the particles and a part which couples to the electrically charged part of the particles. And you see that that's why there is a simple factor for the neutrinos who are electrically neutral, and a more complicated term here for the electrically charged particles. And you see that this is the electric charge here, or 2 times the electric charge of the particles. Okay, but for now, those are all just constants and recipes to be used. One additional word on the history of the neutral charge, of the neutral weak current is given here. So in the 60s and 70s, the standard model was slowly developed, a little bit more slowly than we do in this class here. And there was an hypothesis that there has to be something like a neutral current somewhere, but it has never been observed in nature. And so with bubble chambers, specifically the one Gargamel at CERN, one was able to actually really see those interactions for the first time. And the first pictures have been taken in the 1970s, 1973. And this picture here illustrates, I will explain this in a second, illustrates the interaction of a neutrino coming into the bubble chamber, making an interaction with an electron, and then scattering off, kicking off the electron. So what you see here is this incoming, this is indeed an antineutrino, kicking off an electron. See the electron here. The neutrino goes off undetected, just disappears. You see here the electron. And then there's also 2 photons, one photon here, let's use a different color, and one photon here, causing an electron-positron pair, and the second photon here doing the very same thing. And you can see those particles here, and there's a little kernel here as well. So this is a bubble chamber. Those are bubble chamber pictures. We'll talk about bubble chambers very briefly later in the lecture as well. But they were extremely important and useful tools in order to to visualize and measure particle interaction. All right, so much to the introduction, and we'll continue now with the next lecture on talking about this mixture, this electroweak mixture I was talking about before.